Hello, Algebra 2. This is a lecture on graphing exponential growth and exponential decay models. This is going to be both section 7.1 and 7.2. So there's going to be a decent amount here, but we do get to use two sections. You guys should have a little bit of a background in what it means to be exponential growth or decay, because these terms are used kind of in everyday language, as well as in your science classes and in a math class you probably had before. All right, so an exponential function is a function in this form. This is where we see our variable x in the exponent. Most of the time we've had like x squared or x cubed or something like that, but here we're going to have x in the exponent. Like I said, 7.1 was about growth and 7.2 is about decay, so I've combined these sections. In order to tell the difference between them, exponential growth is when the a value is greater than 1 and the b value is, or a value is greater than 0 and b value is greater than 1. Really, if b is greater than 1, then it's going to be exponential growth, and if b is between 0 and 1, like a fraction, then we're going to call that exponential decay. And whatever the b value is going to be our growth or decay factor. Not a huge deal, but sometimes that term might be used. And in Chapter 7, specifically when we're graphing Chapter 7, we're going to get introduced to something called an asymptote. And an asymptote is an imaginary line that a graph approaches but never crosses. We're going to see this a little bit introduced in Chapter 7, but this is going to be a pivotal part of Chapter 8, where we are continually finding asymptotes of graphs. Once again, I know you guys have seen exponential graphs before, so it's like not much is happening and then it takes off. That's the idea of something being exponential, kind of like something being viral. So this line right here, if I were to take an imaginary line like this, usually graph it dotted, and if this blue line is approaching this line but never crossing it, we would call that this dotted line that I graphed here originally an asymptote. So I'm going to be expecting you guys to graph these exponential functions, and quite honestly, I don't expect you to know how to graph these by hand, other than you could, if you wanted to, do this and plug them in for x and see what you get for y, but we're not really going to do that. We're just going to go right to our graphing calculators and type them in. 1 divided by 4 times 3 to the x power. So there I've typed it in. We can push graph and we can see what that graph is going to look like. As I was talking about earlier, these graphs are going to be level and then take off. That's exponential growth. And exponential decay would be like it starts off decreasing relatively quickly, and then it eventually levels out. So that's what the graph is going to look like. Don't you dare do something like this and call it good. You're not going to get the points for that. Instead, push second, and then table, and get the points from here. -2 is very low, 0.02, so right about there maybe. -1 and roughly 0.1, a little bit higher. 0, 0.25, 1, 0.75, 2, 2.25, and 3, 6.75. That's way up here. I can connect that, and it looks like this. We do have an asymptote that would be right at the axis right here. That's the line that this purple graph is getting close to, but it never actually crosses that line. It never actually gets there. Just forever to infinity gets closer to it. As always, finding the domain and range is going to be really important when we talk about these graphs. The domain, remember, is asking what x values does this graph ever achieve. This graph goes forever to the left, right here, and it goes forever to the right as well. I know it's mostly going up, but it's always moving to the right as it goes up. So its domain is all real numbers, and the domain of every exponential function is all real numbers. The range, however, is always going to be limited. This particular graph, because of this asymptote, and we know this asymptote exists, we know that this graph is approaching that y value, but never actually reaching it. We know that this graph is never getting down here into the negatives. What it's doing is it's approaching the y value of 0, but never quite reaching it. So its range would be y values greater than 0. It is not going to be greater than or equal to 0 because this graph never actually gets there. Like I said earlier, it just forever gets closer and closer to it. Let's look at another one. Let's look at 3 to the x plus 1 plus 2. We're going to go ahead and graph this once again with our graphing calculator. 3, I'm going to clear it first. 3 to the power of x plus 1 over arrow plus 2. There's the graph of it. Of course, we're not just going to estimate it. We're going to push second and then table and get the points from our calculator. At -4, it's just above 2. At -3, it's slightly bigger, but it's just above 2, 2.33. -1, it's up at 3, 0, 5, and then at 1, it's way up here at 11 somewhere. So here's what our graph looks like. The asymptote here, you can kind of get a good idea. You can see it's getting closer and closer to 2. Eventually, this calculator does say it gets to 2, but that's just a rounding error. You can see right here at 2.001, it's getting just really close, and eventually it just says fine 2. It doesn't actually get to 2, though. This is kind of an error in the calculator. It's a rounding error. So this graph gets infinitely closer to 2, but never actually reaches it. Its domain, it goes forever to the left and forever to the right. We know its domain is all reals. Its range, however, would be y values this time greater than 2. Never achieves any y values down here, but achieves every y value from just above 2 and above. If you wanted to know, and maybe you don't, exponential functions could be written like this: a to the x minus h power plus k. K is your vertical shift. It caused the graph to shift up 2. That's why your asymptote's at 2. And it caused this plus 1 actually shifted the graph to the left 1. That's why it's kind of, it's taking off a little bit earlier than some of the other ones. But that's why the asymptote's at positive 2 now. I'm good with the graphing for now. You're just typing it in, getting the information from the calculator. I'm also going to introduce a couple of word problems. Some of the word problems are going to use something called the exponential growth model. And the exponential growth model is y equals a times the quantity 1 plus r to the t. And it's going to go ahead and list what a, r, and t represent. A is going to be the initial amount. R is going to be the growth rate. So it's going to say, hey, it's growing at 7% or something like that. Make sure you turn this into a decimal. T is going to represent time, and 1 plus r is going to represent the growth factor. Now, all of that is true for the exponential growth model. We're going to use that here in a second. There's also something called the exponential decay model, though. There's also something called the exponential decay model. And instead of it being 1 plus r, it's going to be y is equal to a times 1 minus r to the t power. The only difference with the exponential decay model is that our objects, or however many there are, right, there's going to be initial value, is going to be losing a certain percentage for every amount of time. So that would be called then an exponential decay model, and the difference is that we're subtracting the rate instead of gaining the rate. So that's one, kind of two for exponential growth and decay types of word problems that we could see. We're also going to introduce something called the compound interest formula. I love to talk about money, so I would be happy to further talk to you sometime about what it means to have your interest compounded. But this is going to follow this formula. A is going to be equal to P times 1 plus R over N, close parentheses, to the NT power. This is going to be specifically talking about investments, and it's going to specifically use the term compounded. Now, P is going to be your initial deposit here. We're talking about investments. R is going to be the rate, and N is going to be the number of times in a year that your investment is compounded. And really what we're saying about compounded is how often are you paid your interest gains? Are you paid your interest gains just once a year and then you get paid a larger amount of interest? Or are you paid maybe monthly, meaning you get paid that same amount but every month? And so it's roughly a twelfth of the amount as it would be if you gained it for a full year. You're just getting paid more often. Why does that affect the amount of money you make? And that's going to be a topic of discussion in section 7.3, but that is kind of the gist of this formula. So let's use them. First up, we have this word problem. In 2006, there were this many security issues. That sounds like an initial amount to me at a certain company. During the following 7 years, the number of incidents increased by 92%. This doesn't say it very clearly, but per year. Write an exponential growth model. So we know it's growth because it's saying increased. Write an exponential growth model giving the number of incidents. So T is going to be the unknown here. I know it says during the following 7 years, but we're saying in any given year, write a model that would describe it. And so what that's going to look like is going to be using that exponential growth model. Y is equal to A times 1 plus R to the T power. So Y is going to equal 2573 times 1 plus. Now, do not put 92 here. You will be wrong 100% of the time. Instead, you have to turn this into a decimal. You know, to turn a percentage into a decimal, we move the decimal place over twice. So it would be 0.92. 92 here without the decimal would just be insane. It would break your calculator. So 2573 times 1 plus 0.92, and T is our other unknown. Our unknowns are Y, the amount of incidents, and T, the amount of years. So if we wanted to graph this model, we could go ahead and type this into our calculator. 2573 times 1.92, close parentheses, to the power of T, or X, we can just use. Now, we haven't had much experience messing with the window of our calculator, but if I just push graph, we don't see very much of this graph. That's kind of annoying. What I can do is I can push second and then table, and I can still plot the points, and you guys can do a good job of changing your scale and making it work. But I could also mess with my viewing window so I don't only see 10 units to the left, 10 units to the right, 10 units down, and 10 units up. Really what I want to go is a lot more than 10 units up. We know that initially I started with 2500, so seeing just 10 units up is not going to be very beneficial. If we go back to this table, we can see that the Y values are up at like 67,000. And our Y values only go up to 10. And so if I push window and maybe make the Y maximum go up to, let's say, 100,000. That's going to say that the top of my window is now going to see up 10,000 units. And that's a much better idea of what this function is actually doing than 10 units to the left, 10 units up, 10 units down. I probably don't want my window to stay here, so whenever I want to fix it, I can push zoom and then go back to the standard viewing window at 6. But for now, I like it here. How many incidents occurred in the year 2013? 2013 is 7 years after 2006, so if I plug in 7 here for T, and I type this into my calculator, that'll give me that answer. I'm going to do that in a second. And then use my graph to estimate when there would be about 125,000 incidents. Well, I can push the trace button, and I can just kind of drag my little cursor around. And I'm looking for when is the Y value close to 125,000. And it looks like at about 2.4 years, I'm close to, 12,500. If I want 125,000, I got to go way further. I keep going. About 5.9 years. It looks like it's going to be at about 125, maybe about 6 years. So that would be how I could use my calculator to answer a question like this. I'm going to push zoom 6 to get it back to my normal viewing window. And then I'm going to exit out of this by pushing second quit. And I'm going to go back to try to answering this question. About how many incidents occurred in the year 2013. Remember, I'm plugging 7 in for t now. So I have 2573 times 1.92 to the power of 7. So how many incidents occurred in that year? About 2, 4, 7, 4, 8, 5, maybe? Cool. And then let's do one more of these questions. Now we are talking about the other formula. I'm going to go back here and just say we knew that it was going to be this formula because there was no mention of the term compounding anywhere. Apparently my pen isn't wanting to work right now. There was no mention of the word compounding. Then you know to use this formula. In the second word problem that we're looking at, we're going to notice the word compounded. And that is an indicator to use the compounded formula. And we're going to use it twice. One time if it was compounded quarterly. Remember, that means how often are you paid the amount you gained in interest. And in one example, we're going to talk about what if you were paid daily. So either way, we're using the same formula. P is your initial amount, which in this problem is 6,000. 1 plus the rate divided by the number of times in a year it's compounded. So the rate here is 3.13%, but please remember to turn this into a decimal. It's currently in a percentage. So it's not going to be 3.13. It's going to be, move it over 1, 2.0313 over the number of times in a year it's compounded times the number of times in a year it's compounded times 3. And in our problem, we are compounding it in part A quarterly. And of course, if you're compounding something quarterly, that would be to say 4 times in a year. So this is the math that I'm going to need to do. I'm going to show you how to type this into your calculator properly, but be careful with this because this is something that people make mistakes with. So 6,000, 1 plus 0.0313 over 4, close parentheses, to the, and I can type in 4 times 3 here, or I know 4 times 3 is 12. So if I type that in, I would have, this is obviously going to be a money problem, 6588.29. So I started out 3 years ago with $6,000. My account paid me at this interest rate, and 3 years later, I now have, and I wish it was writing clearer. There we go. I now have $6,588.29. Now, what if I'm compounding daily? Of course, if something was compounding daily, that would be to say that it was compounding 365 times in a given year. So I'm going to set this problem up just the same, but it would be 1 plus 0.0313 over 365 times 365. I know that it's writing not very clear, but just stick with me here, times 3. Let's go ahead and try this now. I actually am just going to push second entry and try to edit this to make it work. So I'm not going to divide by 4 now. I'm going to divide by 365, close parentheses. And up here, I'm going to do 365 times 3. Now, some people, if you don't have the little, if your calculator isn't as new as this one and doesn't like go up into the exponent, you have to do 365 times 3 in parentheses. When I push enter here, I'm going to notice my number is a little bit different. It's 6, 5. Wow, you can tell my my computer's just lagging a bit here. 6, 5, 9, 0.67. and that would be how much money I would have if I was compounded daily. So, hope this makes sense. This was section 7.1 and 7.2. Make sure you're trying some problems from this and asking me questions if you have them. Thanks, guys.